Thank you very much for the introduction. So yes, my name's John Davis. I'm a senior scientist at Ilika Technologies, which is an AIM-listed company. Ilika was spun out of the University of Southampton back in 2004, and we've steadily expanded ever since. We now have 35 employees. We focus on, as it says, the high throughput discovery of novel materials. And I'm going to talk a little bit today about some specific work we've done in the area of low-cost catalysts for PEM fuel cells. So, as I mentioned, novel materials via a high throughput methodology is what we do. We mainly focus on the energy and electronics sectors. So in the case of clean tech, we're talking about fuel cell materials, hydrogen storage materials. We also work in areas like battery materials as well. The general way in which we like to operate is to engage with large multinationals from an early stage of a research program, and essentially to undergo joint development programs in order to produce an IP stream that will then provide us with licensing revenue in the future, and that's underpinned by a certain level of contract research that's also performed. So, high throughput materials discovery. Basically what we do, as you can see in the bottom left hand side there, a small electronics chip that's about 35 mil by 35 mil. On that chip we can deposit materials, 100 different materials of 100 different compositions. We then have, basically this is done using a physical vapor deposition system to deposit thin film materials. That means that we can speed up the discovery process by characterizing and screening, also in a high throughput manner, these materials. And in order to actually view all of this and to get out data in a coherent manner, we have an in-house informatics system which can then present this huge volume. You've got to imagine there's a huge volume of data coming out of these systems. So I guess this slide may be slightly over the top for some people here. But essentially what we're looking at is the oxygen reduction process at the cathode of the PEM fuel cells. And we're looking for alternative catalysts which are cheaper than platinum, which makes up a large part of the PEM fuel cell cost. And of course what we're looking at is to try and find a material that is cheaper than platinum and that approaches the activity of platinum. Currently, of course, platinum is basically the industry standard. So as I mentioned, we have these electronic chips which we can deposit our 100 different compositions of a thin film material on. And in the case of our fuel cell materials, we can screen these 100 different fields in parallel in a half cell environment. And out of this, we can get, for example, there's a range of different techniques that we can do, but we can measure the specific activity on each field. Then using our in-house software, we can get, in the case here, it's a ternary plot. So you've got a ternary composition there, and plot on that the specific activity at different compositions. And what you can see quickly is that you can get a hotspot of an active material at a particular composition area. In this case it's a cold spot because it's a negative current, so you see it as a blue area on the left hand side there. Now in the case of the palladium ternary catalysts, Ilika has a published patent in that area for a range of different palladium based materials. And based on that patent, we've been undergoing, as has already been said, a scale-up and commercialization program supported by the Carbon Trust. So that model is slightly different from the model I told you about for commercialization that we use in other areas. So I'll give you a little bit more detail on that. Basically, back in October of 2010, we started with, we partnered with ITRI to scale up these materials. Initially to a supported powder material. Of course, what I've shown you on the previous slides, are all thin film materials. So a thin film ternary alloy. And you can find that you have great activity on a thin film ternary alloy, but then you need to look and see how that will behave when it's scaled up to supported nanoparticles. So we partnered with ITRI, which is a Taiwanese research centre, to scale up these materials to the sort of 10-20 gram scale initially, enough material to perform initial MEA testing. So the MEA testing was done at an independent third-party facility, and that's essentially the stage that we'd reached at by July of 2012. As has already been said, the next stage is to essentially transfer the IP from ITRI to a catalyst company who are capable of doing scale-up of these materials. Because you need, for pre-commercialization programs, you tend to need about 200 to 300 grams. So we want to be able to produce this on a batch of 1 kilogram kind of scale. Then want to do a further iteration of MEA testing to confirm that we basically still optimize these materials and to check that in going from the smaller scale to the 1 kilogram scale, we're seeing the same level of performance. And then the materials will be ready to send out to automotive OEMs for initial commercialization. And we've already had interest from several automotive companies, in fact a couple who provided letters of support for the initial work. And then beyond that, there's further stages which I won't go into in too much detail at this stage. But you can see that the overall model that we have here is that, and this has worked for, or this Ilika applies in more than one field. That we combine the composition IP, which Ilika owns, with the manufacturing IP from a catalyst company, and any relevant third-party IP that comes out in freedom to operate surveys, to produce a final product. That product can then be sold on to customers. In this case, that would mean automotive companies or fuel cell companies. The revenue stream is returned to the catalyst company and royalties to Ilika. So that's the sort of model on which we're operating. A little bit more specifics about the materials that we've produced. So ITRI have made these catalysts supported on carbon. We've confirmed the composition is in the hotspot region that we were looking for material. We've confirmed the alloy of these materials, and also we were aiming for a particle size of less than 10 nanometers to be equivalent to what's in the field. Actually, we've got it's a pretty narrow distribution around about 4 to 5 nanometers. And we've confirmed the activity of these materials in half-cell tests because, of course, we wanted to see that the thin film model basically translated to the alloy particles. The catalyst materials were then sent for independent MEA testing. They were tested according to the US Fuel Cell Council protocols, and the activity was compared to platinum standards. That was through beginning of life tests, and beyond that, we've done some initial accelerated stability cycling between 0.7 and 0.9 volts. So that's 30,000 cycles and 1 cycle a minute. We've also done some preliminary investigations into the effects of loading and some details on ink and MEA preparation, so things like ionomer to carbon ratios, kind of thing. So this is some of the beginning of life tests for one of our particular catalysts. Now you can see there is a lower performance than platinum in the fuel cell. You can see that there. However, basically you've got the US FCC standard states that you compare the power density at a current density of 0.8, and then basically compare that on a cost basis. So we've done these cost comparisons. I should stress that these cost comparisons are done on the cost of the raw metals only. That's the level on which these comparisons have been made. And essentially, while our performance is lower than the platinum catalyst, of course our catalyst is considerably cheaper than platinum in terms of the raw metal components within them. Another standard which has been stated that the DOE suggests that all novel materials, non-platinum materials, should have an open circuit potential of above 0.9. So we also achieved that. We've also done some, as I said, some stability cycling tests. This is an interesting one I put in because if you look, the initial behaviour of this particular MEA was actually not as good as the one I showed you previously. It's a different loading, and there's some sort of mass transport issues. What we've shown here is actually through the course of the 30,000 cycles, the performance has increased back to the level, towards the levels shown in the previous slide. So essentially what we have demonstrated on several different MEAs is that the materials are stable in this potential region over 30,000 cycles. So this is just a quick summary of what I told you. So let's say we've produced some technically promising performing palladium alloy catalysts. They have the potential, this is based on this 70% cost reduction that I showed in the previous slide, the potential to reduce the stacks cost by 26%. As I was saying, this is based on a cost, the raw metal cost, so I should stress that. We've developed a synthetic method to make these materials, and we, as I say, we already have commercial interest from several automotive companies. As I said, the additional program of funding from the Carbon Trust, I've basically highlighted already, but there's the summary of what's going to occur there. Thank you very much.